So our last speaker is Wojciech Nawrocki, who's going to tell us about widgets.
Okay. Yeah, so thank you, everyone. Can you hear me okay at the back with this thing on? Okay, you can. So I will try to give some mix of a demonstration/tutorial on how to extend the Lean4 user interface with visual components called widgets. So I'm interested in formal mathematics and I like proving theorems. So I'd like to prove the following theorem, that Beamer is outdated and we should just do our slides in Lean instead. Let me open up Lean.
This is better work now. What are you going to be in trouble?
So the resolution isn't great, but hopefully you'll be able to see a little bit. So, okay, this is going to be difficult. Try to zoom out a bit. Okay, I guess this is still readable. Yeah, so first, just a brief amount of history of user interfaces for theorem proving. You know, the Lean user interface isn't the first, it's probably not going to be the last. There's a very long and storied history of these things that I won't cover in detail, but I'll upload these slides somewhere so you can click on these things if you're interested. One other source of inspiration is the archives of the UITP workshop that ran until 2018, as far as I know, as well as some reviews written by Ed Ayers and co-authors. And here's an example of one kind of theorem proving interface from the 90s for the Omega theorem prover that is probably difficult for you to rectify now. Now, as far as Lean itself is concerned, the story starts with Lean 3, where Ed Ayers implemented this framework called proof widgets as part of his PhD thesis. And proof widgets allowed you to program graphical visual components for theorem proving directly in Lean. So on the left-hand side, we have an example of a counter widget, which is just, you can click on it and it adds 1 to the state. But the nice thing is that you can write that, in Lean. And then on the right-hand side, we have some example of a clicked rewrite widget, where in the goal state, if you have some sub-expression, then you can click on it and rewrite it according to some group law.
That's not true.
Sorry?
Is that true? Oh, okay. Yeah, that's fine.
No, I think it's fine. Okay, we can discuss it. So then, as far as Lean 4 is concerned, the story is similar, except that Lean 4 is quite a bit more extensible, and you can really change any layer of the stack as you wish. So the syntax itself is extensible via these things called hygienic macros that were implemented by Sebastian Ulrich. And what we can do with this is we can embed domain-specific languages in Lean, such as the HTML tags used to define the contents of this slide. So on the left-hand side, we have some Lean code that is the contents of this slide, and this isn't Lean syntax by default, like you cannot write web pages in Lean normally, but you can change the language to allow for that. And moreover, we can define custom commands, such as the HTML command, which takes some HTML and instructs the system to display that on the right-hand side in the info view here, such as this slide. And similarly, other aspects of the language are also modifiable. And Ed, who's on the left here, and Gabriel, who's on the right, and myself have implemented some extension points for the user interface that allow for this kind of thing that I'm showing now. So the interactive, the environment of Lean is interactive, as we've seen. Outputs of Lean commands are displayed in the info view, which is this panel on the right-hand side here. And what we call a widget is just some user interface component that extends the info view. And for instance, the HTML display thing that I'm using to show these slides is a widget. And widgets are written in a combination of Lean and JavaScript. Functional programmers don't love JavaScript, but it's important to have it because it means we can rely on the large ecosystem of libraries that are out there in the open source community, so that we can do things like this, and we can use the 3JS library to show a Rubik's Cube or whatever it is you want to show to display your mathematical objects or other things that you're interested in.
Can you turn it?
Sorry?
Can you turn it?
Yeah.
Oh, okay, great.
Yeah, you can turn it.
No, I mean, can you rotate the faces?
Right. So,
okay, very good.
You can step through the sequence of moves where you kind of interactively solve it. But There is a variant of this where you can actually use tactics to like change it. Anyway, so another aspect of this enterprise is something called referentiality. And this isn't a new idea, but I think it's useful and important. So let me give you an example first of something in the Rust programming language. So Rust is, I think, known in the programming languages community as, well, at least from the mainstream programming languages, it's one of the best and most informative error messages. And here's an example of an error message that you might see in Rust, where it tells you that basically what's happening is that some type class instance does not exist. So traits are type classes, and trait bounds are sort of like requirements for a type class instance to exist. And in this case, it didn't exist, so the compiler tells you where in your source code you made the error, and which type class is missing, and for which variable it's missing. And but what I wanted to focus on is that below, at the bottom here of this error message, the Rust compiler tells us, well, the type class frog is in fact implemented for this other type. And maybe that's just what you meant. Like maybe you meant to use this type class with this other type rather than the one that you did use it with. And when we think about it, what's happening here is that when writing the compiler, the Rust developers have guessed once and for all, because it's hard-coded in the compiler, which kinds of extra information might be useful to developers when they make this kind of mistake. Right? And maybe it is useful. Like maybe they did just mean to use it with a different type. But in case we need some other information, we are a bit out of luck, because the compiler just tells us this, but it doesn't tell us anything more or anything less. So maybe a better idea is just to allow users to interactively find out whatever kind of information they need. So what happens in Lean is that when we try, for instance, to add to, well, when we write down this ill-typed expression that tries to add 10 to the string ABC, then we will see the error message that says that you cannot, that there is no instance of this type class HADD, which stands for heterogeneous addition, between natural numbers and strings. But the cool thing is that you can just click on this and learn more about addition notation. And if you need to find out other instances, you can click on it and then use the standard tooling to find all the references. Okay, so the difference is that instead of a priori deciding what kind of information might be useful, it just, the environment allows the user to learn it themselves. And this goes back to maybe earlier, but at least from the 80s, there was this PhD thesis by Eugene Ciccarelli, and he called these things presentations. So presentation is a visual or textual display D of an object X with a link back from D to X. So in this case, D would be this piece of text here, and X would be some representation of this term that exists in the memory of the theorem prover server. And in the context of interactive theorem proving, this enables things like this concept of proof by pointing by F. Berthaud and others, where well, we can guide our interactive proof process by clicking on terms that appear in the goal state. And so what I wanted to focus on is 3 example applications of this technology, as well as to give some indication of how you would actually implement a visualization of your own, and hopefully convince you that it's not too difficult. So the first example is in computer algebra. So Tomasz Skrywan at CMU is developing this library called Silene, which is a library for scientific computing. And what it allows you to do is, given say, a system of differential equations written down using real numbers and other mathlib concepts, to automatically or semi-automatically using tactics derive a numerical solver for it. And using the widgets, Skrywan has written a visualization that you can use to see how a physical system with a numerical solver derived for it varies over time. So in this example from Silene, we have some Hamiltonian for a kind of spring-like, wave-like system. And then we can use some tactics that I won't go through to derive a solver. And then we can visualize the results of this, well, so this system is being solved on the periodic domain, and this is being visualized on the surface of the circle, and it's here. But there's nothing happening because it's just a stationary wave, but you can click on it, and then it adds a pulse, and you can see how the wave evolves. So this we can use as a kind of mathematical experimental environment for computer algebra purposes. So that was the first example. Now the second example is geometry. So at Rutgers, Andre Hernandez-Estiet has formalized a synthetic treatment of Euclidean geometry based on this formal system E by Avigad, Dean, and Mama. And also at Rutgers, Wojciech has written a widget to visualize proofs in this in Lean that are using this system. And the technology uses this library called Penrose that is an automatic diagram optimizer to generate diagrams. So let me show you an example of that. So here I have a example proof where given 2 points, we're going to, well, the goal doesn't quite require that, but what we're going to do is construct an equilateral triangle with those 2 points as the base, or rather the line segment between the 2 points as the base. So normally what you would do in, like when writing formal proofs is you would start typing into the proof box here, right? So maybe we do let L be a line of the points A and B, okay? So we can do that and add a line there. But with this widget, instead we can do it visually. So let me click on A and B. And what this does is it shows you all the possible constructions that you can make out of those 2 points. There are 2 circles in a segment. Let me do the circles, because that's what we need to construct this triangle. So we add 1 circle, and then the other circle. And this assumption needs to be changed a bit to go through. Just do that. Okay, so now we have the 2 circles. And the next thing we need to do is to construct the point of intersection. There are 2 points of intersection. But first we need to prove that the circles intersect in order to construct that.
That's what Euclid got wrong, right?
Sorry?
Euclid got that bit wrong.
Oh, did he?
Yeah, Euclid just said, oh, they obviously intersect.
Wow. They obviously.
Don't be very
Hey, dude, look at the picture.
The picture encodes the information.
So, well, in this system, you need to prove this. So,
And then it becomes different.
so I'm going to just use an axiom of the system, which I think those are assumptions, and then some more assumptions, and that works. So now we know the intersect.
Euclid, I hope you're watching.
And now we can click on the intersection assumption in order to get a new fragment here that allows us to insert the points of intersection. So we do that, and now it's intersected those, or at those. Yeah, so we have 1 there. And I guess now the final step is to construct the 3 line segments, which we can also do by just clicking on these guys. So, oops. Click on A and B, insert that. Click on A and this point, and insert that line. And finally, that line there. Oops. It's getting a bit complicated, but there you go. So there's the triangle, and I won't bother with the rest of it. I mean, I'm not trying to prove it's equilateral, but we could go on to do that. So that's the idea of how you might visually construct a proof, or at least make some constructions in geometry. And now I wanted to.
Can you drag the points around?
No. Well, so you mean just to see a different
Yeah,
variation?
to see it move. I mean, if this is too big for the screen, so I want to put
Oh, I see.
it closer together. No, I meant the diagram. Please ignore me. Go on.
Yeah, I think it just doesn't quite fit. You can click this to see different variations on the diagram in case it's not generic enough. So it will randomly sample new diagrams.
Can't have everything free.
And so now, what I wanted to show is how you'd actually implement something, or like a very simple variation of something like this. So there are basically three components to how we do that. First, we're going to have a sort of test bed where we just have an example goal state with three assumptions and a trivial goal. And we will use this to see the results of our visualization. And the useful thing is you can pin this state so that when we change our widget, then we'll see in real time how its outputs are shown. And then there are two parts of the actual widget, which are this thing, a widget module, which is more or less the JavaScript part. So this is the part that's kind of showing up in this in the editor, and that is kind of a web-based piece of code. So I will not modify that, it's just on boilerplate. And here we have the other part, which is just a normal lean function that takes in a panel widget props. And this data structure contains, among other things, a description of the goal. So it contains the current goal as well as other things related to the goal state. And potentially selected locations. So those come in play when you select some points and lines, for instance, like I was doing in the geometry demo. So then this array would contain the stuff that I selected there. And the output of this function is just supposed to be some HTML, modulo the fact that it's in a monad. And so we begin by writing some boilerplate, and let's just return as a test this bold hello world. Okay, it works. You can see it here. And now what I'll try to do is list all the circles that are appearing in the goal state. So how would we do that? Well, first of all, there could be no goals. So if there are no goals, then let's just return something that says no goals. But otherwise, if there is a goal, then we can grab it from the list of goals. And I would explain exactly what that's doing, but it's just getting the first goal. It could be more. I mean, in general, in interactive, they're improving lean and rock style. There can be multiple ones, but I'm getting the first one. Then there's some boilerplate that I will just copy paste, which essentially puts in the monadic computation context that we're writing this function in. Well, it fetches the local context of the goal, because one goal could be able to use these assumptions, and another goal could be able to use some other list of assumptions. So we need to get the right list of assumptions. Yeah.
We really need a function that does this, because I recognize those 4 lines and copy and pasting everywhere, and we really need to have a function doing that.
Yeah, perhaps. And then let me just copy paste more stuff and explain what it's doing.
Interesting.
So first, after we've done the boilerplate, now we have access to the local context, and we can get it using the getLCTX function. And then after some transformations, we can get an array of all the hypotheses. So this will just be a flat list of all the things that we know. And then we are going to start accumulating an array of outputs that our widget is going to produce in order to, well, that will be displayed later. And then we go through the hypotheses, and if the hypothesis is in fact a circle, because this widget is just supposed to find out all the circles, then we will append the circle to our list of pieces of HTML. And li stands for list item, so we're just going to produce these list items. And I will to actually print out this name of a circle, I will use the interactive code component, which is basically the same thing that's used here that allows this kind of interaction of clicking on a type or a term in order to learn more about it. So So you do that. Okay. And now I've accumulated a list of these pieces of HTML. So I should just be able to return a list that splices them like this. And there you go. So there is C, D, E, 3 circles. And that's a very simple widget. So that's all you need to do to kind of start writing these visualizations. Okay, any questions so far? Or can and so the final demo that I wanted to show off is applications of this technology to understand proof automation. So, you know, when doing term proving, some things rely on quite heavy proof automation, and it can be rather difficult to understand what it's doing. Like maybe it succeeds, but you don't know why, or it fails, but you don't know why, or it does something weird. And so it can be good when you use, say, an automated proof search tactic to be able to trace its steps and see, like, oh, it tried to go into this corner of the search space and then failed, and then it tried to go into another corner and succeeded there, and things like this. So we can use these visualizations to do exactly that. So solve by a limb is a tactic that's in Mathlib, written by at least Morrison and Renshaw and other contributors, whose operation is to do backwards style reasoning. So what it does is it will essentially look at the goal and then apply anything that's in the local context, or maybe global symbols if you tell it to do that, whose conclusion matches the current goal, right? So in this case, the current goal is to produce something of type beta. And so the thing we need to do is apply f, because the conclusion of f is type beta. But the problem is that f is parametric over a, and so we need to kind of guess which a to use in order to conclude beta in the end. And there are two a's in the context that can be used. There is a and there is a prime. A prime will work, a will not work, because to apply f you need p1 and p2 of the value that you use. But for the first a we only know p1, whereas for the second a we know both. And so solve by a limb will, in its operation, try both of them, and it will succeed with a prime, but it will fail with a. And we can actually see that that's happening by inspecting this trace here. So to see the trace, you need to set this option, trace meta tactic solve by a limb to true, and then you see the trace. And when you expand it, you see that it starts off by working on a goal of type beta. And then...
How do you see that?
Sorry?
Yeah, okay.
So in the trace here, you can click on the, well, anywhere on here, but there is a like expandable triangle that, does that answer it? Or?
Yes, you should only shortly, but from the context we don't see where it fails, but we can see later.
No, it succeeds overall, but during its operation, it will go into a corner of the space that fails, right? And then it will try something else and it will succeed. But overall, so from the top level, it did succeed, proving beta. So we can expand further to see that it tried to apply the function f, which indeed worked. And it succeeded proving p1 a prime, and then go on to expand, and eventually you see, oh, it tried p2 of a, and it failed. So that's this tick, or whatever, the cross button there says that it did not succeed to prove this particular sub-goal, but oh, it worked. So that's an example of a trace.
Oh, it tries the incidence geometries.
Sorry?
It tries the incidence geometries from the previous question that are still there continuous variable.
Yeah, it is. It does.
That's terrifying.
Well, I mean, anything that's in
Yeah.
anything that's around, it will be tried.
The fact that it's around at all is what's worrying me.
But it's really not type-driven at all. It should have known to just try F and not even try the rest.
Well,
We could expand.
Yeah, well, I don't want to go into too much detail. There should be a discrimination tree under the hood that indexes the types of things that you have available. Yeah, it's a bit weird that it tries the incident geometry.
It's not your problem.
But what I really wanted to show off is just that we can use this user interface to see what the tactic is doing. And what I then wanted to cover is for a different tactic, or a different decision procedure, known as congruence closure. So maybe some people here already know what congruence closure is, just or probably most people do. Very briefly, it's a decision procedure for equational first order logic with ground terms only. So this means the terms don't contain variables, so there's no variables to substitute, and the substitution rule is not present, but we still have the rules for equality, and the only thing that makes this sort of non-trivial is the congruence rule, which says that if you know A equals B, then you also know that f of A equals f of B, and you know that f of A equals f of B, and so on forever. So we need to at least think a little bit about what to do in order to not iterate this process forever and still decide whether some equality holds. And the examples of problems that this kind of thing can solve is, for instance, if we know that f to the 5th power, when you apply it to C, just gives you back C, and f to the 3rd power also just gives you back C, and you can ask, is f the identity? And in this case, in fact, it is. You can prove that it is. So congruence closure is a decision procedure for this, and the way it works is by keeping track, essentially, of equivalent classes of terms. And it does this using a union-find data structure that I could explain, but it's probably easier to show. First, the docstring. So this, the previous picture, as well as the implementation, is based on John Harrison's Handbook of Practical Logic and Automated Reasoning. And as I said, what happens is if we have a list of ground terms, S1 and T1 through Sn and Tn, as well as some goal at whether S equals T, we can decide whether an equality between S1 and T1 through Sn equaling Tn implies that S equals T. And the algorithm I will not explain in detail, but the main part of it is this function called emerge, which adds a new equivalence to the set of known equivalences, or rather updates the data structure that stores these equivalence classes by merging some equivalence classes together. Well, it can be, I don't know, maybe it's not clear what it's doing, so let's try to visualize it. So if we start with an algorithm like this, which is just the kind of basic implementation, let's see what we have to add to see a visualization. So there are two lines, basically. The first one is this one, lean.with trace node, which will add a node to the trace, which is easier shown. So I will go down to an example, maybe this one, and in the example. And so this with trace node invocation basically caused these nodes to appear in the trace. And so these are all the equations that the algorithm is merging during its operation. But it's still not, I don't know, maybe this isn't super clear to read, and we don't know what the equivalence classes actually are. So let's visualize that. And to do that, we add these lines here. So what these lines are doing is the trace macro is, well, adding a trace to the trace, or adding a message to the trace. And in the message, I will just take the EQV variable, which is the set of classes, turn it into HTML with some function that I have previously written that I will not go through. And then we just put that HTML in a message with some fallback text in case it fails to be displayed. And now we can click on this and see these equivalence classes. So the first equation, we just have f to the 5th power pointing at C. So in this case, C is the chosen representative of this equivalence class, and f to the 5th power is some element of the equivalence class. Then after we add another equation, and now we know that in this equivalence class we also have f to the 3rd power, which is pointing at the same canonical representative being c. So the root of this tree is the chosen representative. And then we add more equations. In this case, an equation was added that does not involve any of the terms in the already known class, so we add a new class to the forest. Now there are 2 classes. And so on to until eventually everything is merged into a single equivalence class, and in fact this class implies the equation that we are trying to prove, which is that, I think is this one, which is that f of c equals c, right? So right here, f of c and c are in the same class, so prove it. Yeah, and you can use this to also show, to also visualize an example where it fails. So at the end of the process, I think we should have here two classes. And that implies that the equation that we're looking at does not hold, because f and c are in different classes. Okay, so that's what you do to visualize some proof automation or a tactic. And conclusion. So some scattered thoughts. There are many people whose work we build on, and some even use ours. This is only possible thanks to the many people in the community and the Lean development team. Recently, especially Mark Rusinga has been helping a lot with the the editor extension. This takes a lot of inspiration from kind of 80s and 90s graphical interfaces for Lisp, Smalltalk, as well as Nupril and the Idris theorem prover / dependently typed language. Yeah, rich type systems deserve rich programming environments. Thank you.